Hello everyone. In this video, I will share you about the ultrafast magnetism. With this outline consists of the magnetization dynamic, Landau-Lifshitz-Gilbert equation, ultrafast magnetism, time-resolved magneto-optical Kerr effect, 3T-M model, ultrafast magnetism, terahertz emissions. And let's move on. Here is the range of the terahertz and the gigahertz. Here is the magnetization dynamic. And as we know that the 1 terahertz correspond to the 1000 gigahertz and 1 terahertz also correspond to the wavelength 300 micrometer, and also the photon energy is the 4.1 milli electron volt. And of course, the time scale is correspond to the 10 to the power of the minus 12 seconds. So you all know where we are in this spectrum, and there's radiation have shown unique properties, and this radiation provide a variety of application and opportunities in different fields. Here we introduce you some of these aspects briefly. There's radiation are capable to penetrate a wide variety of non-conducting materials. For medical, there's radiation can do screening method. Recently, it received extensive attention as powerful tools for the early detection of cancer, since they provide dielectric contrast for imaging and not ionizing. Third, imaging has proposed novel feature in diagnosing different deficiencies in teeth, skin, breast, and solid organ, which are not apparent with other imaging methods. There are unique properties of the radiation that make it an interesting technique in the pharmaceutical and security application also. Detection and imaging of drugs, explosive and bioagents, non-destructive and non-invasive testing and inspection, pharmaceutical and foodstuff quality control, and medical diagnostic are other applications related to the terahertz spectroscopy. Using the Earth's carrier in secure communication has led to some advantage, namely small antenna size and large information bandwidth. Lower scattering and much greater penetration through the aerosol and clouds have made the terahertz signal more favorable compared with IR and optical wavelength for communications. And the other one is the data bit storage. This is very useful nowadays because people always try to increase the density of storage with make higher capacity and smaller size. And then now people can use terabyte data with faster writing and reading the data. So this all application people still working in the terahertz regime. And this figure shows the time scale of various dynamical processes in the magnetization. The fastest process here is the fundamental of the exchange interaction. It occurs in the time scale 1 femtosecond to 10 femtosecond, and then followed by the spin orbit coupling and spin transverse torque in the 10 femtosecond to 100 femtosecond, and also the laser induced ultrafast demagnetization occurs in the 100 femtosecond. And then the precisions in the 1 picosecond to 100 picosecond, and followed by the damping. This is very important, and this has happened in the order of the nanosecond, and the longest one finally is the domain wall motion. So here we will see the change of the magnetization dynamic with these time scales. We can see this time scale. In the terahertz regime here, it corresponds to the picosecond here. The time is the picosecond, so the laser induced ultrafast demagnetization, it happens here. And let's move on. Here is the Landau-Lifshitz-Gilbert equation. This is named after three persons. In 1935, Landau-Lifshitz here predict the rotation of the magnetization in response to the torque. And here is the magnetization. The blue line here is the effective field. So if we apply the effective field, the magnetization will experience the torque with this magnitude, the torque, but it will not align to the effective field. So in the 1955, Gilbert tried to complete the equation by adding the damping here. So when we apply the effective field here, and the magnetization will experience the torque, and by the time they will align with the effective field, so they will be aligned with the effective field. So we need the damping here. This is very important. So this is the equation for the Landau-Lifshitz-Gilbert equations. It shows two important terms here. The precession term here, which correspond to the torque of geomagnetic movement, and this one is the damping term, which lead to the magnetic moment aligned to the effective field. Damping determines how fast the magnetization relates towards the effective field. Without damping, the moment would never be able to align itself with the applied field. So the damping here is the alpha. It can be contribution from the intrinsic damping, from spin orbit coupling, or from the phoneme magnet scattering or eddy current. And for extrinsic damping, it could be contribution from the inhomogeneities. So here you may see the effective field here, or this the Hamiltonian is consists from the exchange interaction, anisotropy interaction, demagnetization interaction, and also the Zeeman. Here, the exchange energy is kind of the energy that try to align neighboring atom. So exchange interaction between the spin of the two atomic moments are responsible for the magnetic order. This interaction play a fundamental role as the type of the magnetic order that occur depend on the sign of the exchange interaction. And the other one is the anisotropy. Here, anisotropy is the directional preferential of the magnetic properties. So it could be contribution from the magnetocrystalline anisotropy, which is a phenomenon in which the internal energy varies by the direction of the magnetization in the materials. It could be uniaxial anisotropy or cubic anisotropy. And the other anisotropy is the shape anisotropy. The shape anisotropy is related with the magnetostatic energy. And the other one is also the magnetoelectric anisotropy and external stress. If you give stress, then the sample will change the anisotropy. And the other one is the demagnetization energy here. The largest contribution to the effective magnetic field is provided by the demagnetization fields, here responsible for the domain structure formation in the magnetic field, because the demagnetization will minimize with creating the domain. So they are very important. And here is the Zeeman energy. Here Zeeman energy is the potential energy of the magnetized body in an external magnetic field. And here is the ultrafast magnetism, time resolved magneto-optical carrier effect, or TR-MOC here. And the first observation of the magnetization dynamic on the sub-picosecond timescale was made by the Professor Berer et al. In 1996, as reproduced in this figure. And this is the time delay in the order of the picosecond, and this is the normalized remanence. So here, experimentally, it was found that a nickel thin film can be demagnetized in the sub-picosecond timescale after excitation with a 100 femtosecond laser pulse. So they shows this kind of the graph, and it represents the change of the demagnetization with a delay time here. And they see this kind of the figure using the TR-MOC. This is the schematic of the TR-MOC, as you can see here. TR-MOC used to measure the magnetization of sample at a different delay time after a femtosecond laser excitations. So here we can see more intense part. This pump is the more intense part. This is about 90% of the total energy to excite the magnetic moment and trigger the magnetization dynamic. And the black line here is the probe beam. Is this one is the less intense. We call it as a probe. It's about 10% of the total energy. And this one to detect the rotation in polarization of the reflected beam via MOC. And this between the pump and the probe beam, they have the different time. They have the delay time, delta t here, but both of them will overlap to hit the sample here. And in this figure B is the schematic result of the TR-MOC magnetization as a function of the delay time. And this one is the delay time in the order of the picosecond, and this one is the normalized of the magnetizations. And they represent the different stage, indicate in the different number. This is the stage 1, this is the stage 2, this is the stage 3. And when in this stage 1, it happen occurs in the time delay less than 0 picosecond, or you can see in this figure, it's more clearly where we have they are still in the equilibrium because the femtosecond laser is not hit the sample yet. So they are still in the equilibrium. Magnetization doesn't change in the stage 1 here. And the next one is the stage 2 here. They differentiate between these stage 2A and the stage 2B. Stage 2A is when the time scale is equal to 0. Then they try to change the equilibrium here, and it indicate as a theta c prime. This is the original condition, and then after the femtosecond laser hit the sample, then they change the equilibrium becomes this. And then this 2b is the when the time delay between the 0 to 10 picoseconds. Then in this stage, is shows that due to the heating, anisotropy is changed. So uh, they try to rotate to new equilibrium here to theta c prime here. And the next one is the stage 3, where the time scale is more than 10 picosecond. In this stage 3, the heat already diffused away and the magnitude of M and anisotropy are restored. So they are processed in the new equilibrium here. They make the new equilibrium here in this stage 3. So that's all about this TR mock. And next we go to this 3 temperature model, or we call it as a 3TM. But before going that, we will introduce you these things. This one is the ferromagnetic layer, and this one is the non-magnetic layer, where we hit the ferromagnetic layer with the femtosecond laser, and it will generate a spin current, a flow of spin. This is the key concept of the field of the spintronic. And we call pure spin current, which is a spin current without accompanying by the charge current. And one of the ways to create pure spin current is by the spin pumping in the materials with strong spin orbit coupling. So this one, spin pumping, will after hit the sample with the femtosecond laser, they will precess, the ferromagnetic layer will precess, and then they will transfer the spin angular momentum across the interface to a non-magnetic metal here. So they will generate the spin current. And this one is the 3 temperature model. The 3TM is the extension of the 2 temperature model, 2TM, which is used for describing the experimental investigation of the picosecond laser pulse excitation in normal metal. And in this 3TM, it assumes that the system consists of the 3 thermalized reservoir for exchanging energy, namely as the electron, here is the lattice, and the spin. So they make the equilibrium between these 3 things, and it connect each other with this with this G. G is the interaction constant. This is the interaction constant between the electron and the lattice. This is the interaction constant between the spin and the lattice, and this one is the interaction constant between the electron and the spin. So in the 3TM, it has the different temperature of the electron, temperature of the lattice, and temperature of the spin. After the pump laser excitation to the magnetic film has non-equilibrium electron distribution, and it cannot describe by the Fermi-Dirac distributions. So the absorbs energy from the femtosecond laser will create the hot electron within the system. And the 3TM describe the process of the making energy equilibrium during the ultrafast magnetization and recovery of the magnetization back to equilibrium conditions. And this one represent in this equation. So this one is the specific heat of the electron with the differential temperature change with respect to the time, and this is with the difference of the temperature, and this PT is the laser source term. And This one has the specific heat of the spin, lattice specific heat with the different temperature. So they connect and to make new equilibrium after the femtosecond laser hit the sample. And let's move on. And here we comes to this ultrafast magnetism with terahertz emissions. And observation of, as we know, observation of the sub-picosecond light-induced demagnetization in the ferromagnetic nickel 2 decades ago by Professor Berer can be considered as a key towards ultrafast spintronic. A pump probe approach is most commonly used, and in this figure, we can employ the dynamic is accompanied by the emission of the electromagnetic radiation at terahertz frequency. Recent demonstration of ultra-short laser-induced currents via spin-orbit coupling using only terahertz emission spectroscopy shows the potential of this technique for developing ultra-fast spintronic. Here you have the magnetic metal. You hit the magnetic metal with a pump laser pulse here, then you can generate this kind. You can get this magnetization as a function of the delay time. You can also get the conductivity of the materials as a function of the delay time, and you can also get the current as a function of the delay time. This dashed black line, this one, is represents when the laser hit by the pump laser pulse. So this one is still equilibrium. So after the laser comes, so this one represents as the dashed black line here. And as an example of the terahertz emissions, we consider a slab of a material. This is the slab. With the coordinates as shown in this figure. This is the y-axis and this is the z-axis. We know the width of the slab here is from 0 to L. The width is L here. So you hit the sample, you hit the ferromagnetic material here with the pump laser pulse. So the pump laser pulse will hit the sample and they will generate the current, and then the pump laser pulse can be reflected here with these equations. So you can see here can be reflected where the z less than 0, and then it can be absorbed, they absorb with this thing, and it can also be emit with this kind of the equation, and it will generate the terahertz radiation. And this one, the emitted amplitude at this limit is given by the Ohm's law. So we can see the amplitude, the D amplitude one, it's related to the Ohm's law, so we can get the conductivity of the materials with this Ohm's law. So here is the equation by considering the boundary condition, then you can get this kind of the emission of the pump laser pulse. Okay, and then another one here. So here is the schematic of the terahertz emissions. This is the schematic, but in the simple way. Actually, in the real, they have more complicated schematic. But here I just show you the simple thing, so it's easy to understand. This blue line here is the terahertz radiations, and this red line here is the probe laser pulse. So both of them has the different time, so they will have the delay time. They will hit the sample. This is the ferromagnetic sample, and this one can be change of the electro-optical properties here by varying the arrival time. So they can reconstruct the electric field of the terahertz radiation in time. These parabolic mirror are commonly used in order to overlap the laser pulse and the terahertz radiation. So they must be overlapped in the one point in the sample. And this is the kind of the results of the terahertz emissions. This is the electric field as a function of the time here. So you can see here, this is the when they emit, they have the peak here in this time. So you can see the time when will they emit, and then from this result we can also get the, from this time domain, we can also get the frequency domain here in the terahertz range. And here using the fast Fourier transform or FFT, and from this frequency domain we can see how much the frequency our sample is. In this range are larger or smaller, so we can see the frequency domain of the materials from this kind of the measurement. And if you have the ferromagnetic materials and this one is the non-magnetic materials, so you stack them together. So you have the adjacent layer here is the non-magnetic materials, and you hit the ferromagnetics material with ultra-short laser pulse, and ultra-short laser pulse here will initiate the injection of the spin polarized electron here, so they will generate here. In the ferromagnetic materials here, they will generate the spin current here, and they also will generate the charge current in the non-magnetic materials, and this charge current will generate the Terra's radiation here. So illuminating a ferromagnetic metal layer with ultra-short laser pulse creates hot electron. In this way, it's possible to inject spin polarized electron into an adjacent metallic layer on a sub-picosecond time scale. If this adjacent layer has strong spin-orbit coupling, the inverse spin Hall effect can subsequently cause the paths of the spin-polarized electron to deviate depending on their spin direction. So it depends on the depend on the inverse spin Hall effect. So subsequently, the inverse spin Hall effect causes the path of this electron to deviate, and they will generate the charge current here in the plane of the sample, and this charge current can give rise to the emission of the terahertz radiation. So here is the terahertz radiation what we can get here, and this terahertz radiation is corresponds to the charge current and correspond to the spin current, but it has perpendicular to the magnetization here. So that's all what I can say in this presentation. I hope you enjoy this presentation and see you next time. Thank you so much.